Chapter 3. I do like the quote at the beginning of Chapter 3 of your textbook. No great work is ever done in a hurry. So I advise you take your time, be careful with the problems in this chapter. Um, these, Everything that you do that's um, of great scientific discoveries, it takes a lot of time and patience and perseverance. I can vouch for that. Anyway, so this chapter is method of analysis. You should probably think of this as the most important chapter in the book. Your textbook actually says it's the most important chapter. And you've already been actually applying some of the concepts in the last chapter. But in this chapter, you will formalize more procedurally the methods that you can use to analyze the problems that we were doing in the last chapter and even bigger circuit problems that are in this chapter. So the two main methods of analysis used for the rest of this textbook are nodal analyses and mesh analyses. Nodal analysis uses the nodes, which you can see in Kirchhoff's current law. You are always looking at a node and current into the node and current out of the node. So KCL applies to nodal analysis. Mesh analysis uses KVL, Kirchhoff's voltage law. So you can analyze any linear circuit with these techniques, and I will emphasize a linear circuit works with these techniques. Also in this chapter we are going to use math programs to help us to solve the problems because the problems are becoming larger now. I'm going to use MATLAB because UH Manoa uses MATLAB and a lot of engineering schools do use MATLAB. I personally like a math program called Mathematica better, maybe because all my grad school work was using Mathematica. But in either case, you can use program of your choice. You can use also Maple, and I think there's other math programs available. You can also use a programmable calculator or your graphing calculator to solve these problems. So I will use MATLAB to introduce you to MATLAB. MATLAB is a scripting math language, so it's a little bit run like you're writing a program. So if you're in programming classes, you will see that MATLAB is a little bit like writing a program. MATLAB is used in industry. When I worked as a research scientist, I used MATLAB a lot to process a lot of data and analyze a lot of data. So MATLAB is not just an academic thing. MATLAB is a professional math program. You can buy the student copy for $50 from mathworks.com. I actually quite highly recommend it because you will probably use it quite a bit over the next few years studying to be an engineer. I will also use circuit analysis programs in this chapter. I, on this campus, have Multisim, which is a National Instruments product. You can also buy a student version of Multisim. I think it costs $40. I highly recommend it. Multisim underneath is a PSpice simulation. This textbook does talk about using PSpice. You can use PSpice in a very textural, meaning text, in a text environment. But it's nice when it becomes graphical, where you place resistors, place capacitors, place inductors, and analyze the circuit that way. So I may be using Multisim, except that my video recording software doesn't exist on the computer that Multisim is located at. So I have to figure that out. We will also look at some free downloads, maybe look at some free downloads of other software. Okay, moving on. Nodal analysis we're going to talk about first. Your textbook has steps to do nodal analysis. We were already doing nodal analysis in the last chapter, although it wasn't formalized. So the steps are basically select a node as the reference node. Point out a few things. So selecting a node as a reference node is sort of like I was already doing in the examples last chapter. First, identify all the nodes in the circuit. I see node 1 is there, node 2 is there, and I see there's another node down there, But I'm going to say all my voltages are relative to this node, so I will put in a ground point and call that 0. And then out of convenience, I will also say that that's node 0. So my nodes have been numbered here, 1, 0, 1, and 2. Instead of writing this ground symbol, which is an earth ground, I could have written a symbol that looks like this. This is called a signal ground. And then there's one more symbol, this one, which is called a chassis ground. So sometimes this 0 reference point is tied to the chassis, which is like the metallic box that holds the electronics. That's your chassis. Your computer housing, that's a chassis. And the circuits inside are tied to the chassis. But then oftentimes the circuit is also, the chassis is then tied to earth ground. So earth ground is literally in your building, a pipe into the ground, and everything that's tied to earth ground, like your green wires in your light fixtures, everything that's tied to earth ground is literally to the earth. So the earth is a good 0 reference starting point. So I am going to, I could pick anything, but I am going to call this node, node 0, my reference node. So all the other voltages in the node are relative to this reference point, so I call this 0. So then it says assign voltages to the remaining n-1 nodes. I have n nodes, n is 3 in this circuit. I am going to assign voltages to each of the other nodes, n-1. All of the nodes except this one, because this one's at 0. Voltage at node 0 is 0. So this would be voltage at node 1 is right here, and this is voltage at node 2 right at this node. So okay, so that's good. And then it says apply KCL to the remaining n-1 reference nodes. Use Ohm's law to express the branch currents in terms of node voltages. So I'm going to do KCL at each of the nodes, and I'm going to use the conventional current flow convention. That means in a passive element, such as a resistor, current flows from a higher potential to a lower potential. That's what the textbook says, but essentially it means to establish what your current flow direction is. So if I say that current is going here, I make an assumption that V1 is greater than V2, and then I'm going to put this potential is higher than this potential. It's somewhat of an arbitrary assignment because you don't know until you analyze the circuit if voltage at 1 is truly higher than voltage at 2, but I have to make some assignments in order to analyze this circuit. So make some decisions. Now, I'm pretty sure voltage at 1 is going to be, it could be lower, but voltage at 1 is higher than voltage at 2. I'm going to make an assignment of current flow. I'm going to put plus here, minus here. So when current goes into the resistor, there's a plus sign, and then the other side will be a minus sign. Similarly here, I'm going to put a current there, and I will put the plus sign there and put the minus sign there because the current is going into the resistor, so the side that goes into is at a higher potential than the side that it exits. Now keep in mind, electron flow is actually opposite. We are talking about this conventional current flow method. So then it says write all of the node equations in terms of these voltages at the nodes. Right, so the node equations is an application of Kirchhoff's current law. And then solve the remaining simultaneous equations to obtain the unknown node voltages. So I'm going to go on to the next slide where I have a little bit more room. There's my next slide. So I will put my currents back on. I1 goes in. I think your textbook has a little funny notation in it. I think they call this a little I1. Let me check real quick. Your textbook calls it a little I1, a little I2, and a little I3. So I think that's a little bit, I like calling I2 to go with R2 and I1 to go to R1, but I don't like having the capital I1 and capital I2, but that's what your textbook did. So we'll go with it. We can do that. So then I established that I2 goes this direction, so I better put a plus sign there and a minus sign there when I write my node equations. So let's write the KCL at node 1. So if I write KCL at node 1, I have current going in and 2 going out. So current in equals current out. I1 equals I1 plus I2. And then I1 equals, now I can write I1 as voltage here minus voltage here divided by R1. So I can write it as voltage at 1 minus the voltage at 0 over R1. And I can write I2 as voltage on this side minus voltage on this side, so voltage at 1 minus voltage at 2 divided by R2. And voltage at 0 is 0 because I called it 0. That's my reference point. So I get I1 equals 1 over R1 plus 1 over R2 V1 minus 1 over R2 V2. So I wrote one equation. It turns out that these n minus 1 nodes, so there's 3 nodes, you don't count the 0, 1. It turns out that I need 2 equations to solve for my 2 unknowns, voltage at 1 and voltage at 2. So if there's 2 unknown voltages, then I need 2 equations to solve this problem, to completely analyze this problem. So let's do KCL at node 2. I get current going in plus current going in equals current leaving the node. So I2 equals what's plus. So little I2 is keeping my convention. It's V1 minus V2 over R2 equals I3. So I3 is V2 minus V0, which is 0, over R3. And so then I rearrange some terms here, and I get I2 equals V1 minus 1 over R2 plus V2 1 over R2 plus 1 over R3. So between here and here, I now have 2 equations and 2 unknowns. And so it's a matter of solving these 2 equations, and which you can do by substitution methods, 2 equations, 2 unknowns. You can solve it by Cramer's rule. You can solve it by math programs. So let's do a numerical example. Actually, before I go on to my numerical example, once I solve these 2 equations, I find out what V1 is. It'll be some voltage, and I'll find out what V2 is. It'll be some voltage. And then I can go back, since I know the voltage is at 1 and the voltage is at 2, I can go back and solve for the other currents, I1, I2, and I3 from these relationships. And then the circuit is completely analyzed. Okay, so now let's do numerical example. Okay. I am going to somewhat arbitrarily call this node 0 down here. Node 0, voltage at 0 is 0. That was my reference point that I decided. I'm going to go through and find all the nodes. There's a node at 1, here's a node at 2, there's 3 nodes, 1, 2, 3, but one of them's at 0, so I have 2 nodes I don't know what the voltage is, 2 nodes and 2 unknowns. I'm going to have to write 2 nodal equations. So let's do we're doing nodal analysis, KCL at node 1. We'll do that. So I have to make some decisions here. I think I will call this I1. I think I'll change my mind there. I think that I will call ooh, wasn't paying attention. I think that I will call can name it's somewhat arbitrary. I'm going to call this one I1 because it's already known. I1 is 5 amps and 5 amps everywhere here, both these in and out of the nodes. I2, I am going to define it as being, guess it to be that direction. I'm going to guess I3 to be that direction. I'm going to say that this is I4, so it equals 10 amps. And then I'm going to say this is I5, and again I'm going to guess it to be that direction. So now I've made some assumptions of directions. I need to label my polarity markings. So current goes into the resistor, and then it is at a lower potential exiting the resistor. So into gets the plus, out of gets the minus, into gets the plus, out of gets the minus. So I'm saying that this voltage is higher at a higher potential than this voltage. That's my assumption, that's my best guess, and now I'll analyze the problem and see what it comes out to be. So at node 1, I get out, out, in. I get I1 equals I2 plus I3, or 5 equals, what's I2? I2 is voltage at A, or voltage at 1, minus voltage at 2, because this voltage is higher than this one, and you need the difference, divided by 4 ohms, plus I3. I3 down here is voltage at 1 minus voltage at 0, which is 0, divided by 2 ohms. So I1 equals I2 plus I3. Multiply both sides by 4. So this was at node 1. So now we do the same thing at node 2. I have I2 going in plus I4 going in, 10 amps, equals current going out, which is I5, and the other current going out is I1. So I2 is voltage at 1 minus voltage at node 2 divided by 4. I4 is 10 amps. I5 is given already, 5 amps. And I1, whoops, I5 is not given. So I5 is this one right here, which is voltage at 2 minus 0 over 6 ohms, plus I1, and I1 is 5 amps. So rewrite that equation, make it prettier. So let's say this is 5 on this side equals V2 1/6 plus 1/4, and V1 is a minus 1/4. Yeah, wait, V2, yes. V2 is a plus. Yes, yes. I'm going to go ahead and multiply both sides times 12. 12, yeah. 12 times 5 is 60 equals V1 times 12. Both sides times 12, so I can simplify. So that one's V1 times 3, negative 3, plus V2, 2 plus 3. So I have 60 equals minus 3 V1 plus 5 V2. So this is at node 2. So I now have 2 equations and 2 unknowns. That's one of them, and the other one was 60 equals so 2 equations, 2 unknowns. I can solve this by conventional methods. I can just go ahead and add these 2 equations up. So that's a 20. I get 80 equals 4 V2. So therefore V2 equals 20. And then I can substitute V2 back into the first equation. 20 equals 3 V1 minus V2. And I said V2 was 20. 20 equals 3V1 minus 20. So 3V1 equals 40. Therefore, V1 equals 40 over 3 volts. So now I know both voltages at this node and at this node. And using these relationships, I can go back and find the various currents. Equals 13.33. Okay, so this one I made my 2 equations and 2 unknowns, and then I substituted. I just substituted one equation into the other, or did a subtraction here so that I could solve for the 2 unknowns. That's not the only thing I could do. What I could have also done is apply Kramer's rule. You guys have probably learned Kramer's rule somewhere before. Let me get my 2 equations here. Try again. Get my 2 equations. Come on, get my 2 equations. Doesn't want to select that second equation. Okay, let's rewrite it on the other side, next slide anyway. So please select. Okay. It's fun to learn to use my new tools. Not that new anymore. So I like this equation was a correct equation. This one I don't want. And the other equation that was, let me go back and see, was 60 equals plus 5E2. Okay. And that is a 20 there. So quick review of Kramer's rule. I can rewrite these 2 equations right here in matrix form. And so if I want to write it in matrix form, I see that this is, you look at the coefficients of these unknown variables that you have. I have a 3 and a -1, and I have a -3 and a 5, and then my two unknowns are V1, V2, and that equals 20 and 60. So just to refresh you that it works, how this works when you're multiplying a matrix, this is a 2 by 2 matrix, and this is a 2 by 1 vector, 1 by 2 vector, and this is a vector. So if you were to multiply this out, you have this times this plus this times this, so that is 3v1 minus v2, and it equals 20. So you get back that. So row times column equals a number, a scalar number, we say in vector notation. So row times column, you get a vector. This row times this column, you'll get the other scalar answer. So this -3 times this plus 5 times this, and you get that. So you get these two equations back, but I'm instead expressing it in matrix notation. So when I have matrix notation, I can use Cramer's rule to solve for the unknowns v1, v2. So first thing you have to find is the determinant of the matrix, which is given a symbol delta for a determinant. And so this is the determinant symbols, -3, 5. And so it's this times this, 3 times 5 minus this times this. So 3 times 5 minus 3 times -1, and that is 15 minus 3, so equals 12. That's the value of the determinant. And now you want to find v1, v2. So v1 equals the determinant 1 over the main determinant, this one that we just solved. And this is determined by, if you want to find v1, you take out this first column of information, this 3 and -3, and you substitute this in. So I'm going to do this. I'm going to take out the first column, and I'm going to put a 20 and a 60 in there. Keep the second column the same. And this is actually the same determinant that we just calculated, but I'll write it down to be explicit. And so we already know that this is 12, and you find the determinant of this numerator part right here. It turns out to be 160, and then V1 is 13.333 volts. Same answer that we got before. You do the same thing for V2. V2 is determinant 2 over determinant of the denominator. So we already know that is 12. This time you put the first column back, and we're finding number 2, so you substitute the second column in, 20 over 20 and 60, and you compute that determinant, and you will get 240 divided by 12, which is 20 volts. So same answers that we got before, and then you can go back and calculate the currents if you want. So that's Cramer's rule. Now we can extend that to bigger circuits that have more nodes, and these matrices will grow in size. The number of equations and the number of unknowns will grow, and at that point it does become nice to use a math program. Okay, so let's look at a bigger problem now. This is example 3.2 out of your textbook. I'm going to go ahead and use the currents that they've already marked on here, but I'm going to put my sign convention on here to make sure I get the signs right. So current is going in, that must be plus, that must be minus, that must be a plus, that must be a minus. Current goes in, that's a plus, that's a minus. And then we have a dependent current source. So the current of this node depends on the current that's going, the current of this branch depends on the current that's in this branch. So we'll have to account for that. So now, okay, so I have a node here, a node here, a node here, and I have a node here, voltage at 0, which I decided that that's my 0 reference point, so there it is at 0. Okay, now we go and write the node equations. At node 1, we have current going in equals out plus out, so I have no name on that one, but I have 3 amps equals I1 plus IX. I can go ahead and write what that is. So I1 is V1 minus V3 over 4 ohms. V1 minus V3 over 4 ohms. And IX is V1 minus V2 over 2 ohms. And I know that I'm going to end up having to solve for V1, V2, and V3. So probably nice to just make those nicer numbers. If I multiply both sides by 4 and rearrange the terms, I will end up getting that 3 V1 minus 2 V2 minus V3 equals 12. So I multiply both sides times 4, and I get a nice node 1 equation. Now I have 1, 2, 3, 4 nodes, which means I need 3 node equations to solve this problem, and there will be 3 unknowns, which are V1, V2, and V3. So let's do at node 2. Node 2, you have node 2, I have IX as it goes in equals out, out. So IX equals I2 plus I3. So I2 is V2 minus V3 over 8 ohms. And I3 is V2 minus V0, which is 0 volts, right, over 4 ohms. And so I'm going to clean up this fractional stuff, multiply both sides times 8, and I will get minus 4 V1 plus 7 V2 minus V3 equals 0. It equals 0 because this node doesn't have any of these known current sources involved, so it will equal 0. So that's at node 2. And then at node 3, I have node 3 right here. I have I1 is an in, I2 is an in, and this dependent current source is an out. So I1 plus I2 equals dependent current source, which is 2IX. And I do have an expression for IX already. Remember that IX was right here. This was IX, V1 minus V2 over 2 ohms. So I make the substitutions for what IX is. So I1 is V1 minus V3, V1 minus V3 over 4 plus I2. I2 is V2 minus V3 over 8 equals 2 IX, and IX was V1 minus V2 over 2 ohms. So multiply by 8 and rearrange the terms, and I will get 2V1 minus 3V2 plus V3 equals 0. So now I have 3 equations and 3 unknowns, V1, V2, and V3. Now I can use solve for three equations. So, which are V1, V2, and V3. I have choice here. I can do process of elimination to solve. That's solving for one variable at a time, substituting it into elimination, substituting it into other equations. A bit tedious. Hopefully you should all remember how to do that. Or I can use Cramer's rule again. And the third way I could solve it is, since I have these three equations and three unknowns, is I can use a math program. So I'm not going to show you tedious process of elimination. It is in your textbook, page 86. It's probably worthwhile a little bit to refresh Cramer's rule, so I'll go over some Cramer's rule, and then I'm going to show you the math program, and you'll say, oh, that's so much easier. So go ahead. So my three equations and three unknowns right now are, I'm going to repeat them real quick. 3 V1 minus 2 V2 minus V3 equals 12. That's one equation. At node 2 we got minus 4V1 plus 7V2 minus V3 equals 0. And at node 3 we have 2V1 minus 3V2 plus V3 equals 0. So these are our three equations and our three unknowns, V1, V2, V3. We can write that in matrix form. So 3 minus 2 minus 1 minus 4, 7 minus 1, 2 minus 3, 1. Put it in some matrix brackets. My unknowns in order, V1, V2, V3 equals 12, 0, and 0. So if I want to apply Cramer's rule, I need the determinant of this matrix right here, the determinant of that. So the determinant of that, there's several ways you can do it. There's one where you block off, do 3 times determinant of this. There's a few different ways. So I'm going to work with it as a 3 by 3 matrix. So it's a 3 by 3 matrix. And I'm going to work with it that way and find the determinant. So determinant of that, you write 3 minus 4, 2, minus 2, 7, 3, minus 1, minus 1, 1. It's interesting, when I learned how to do this in school, I then took these first two columns and repeated them over here and did the multiply out process. Your book takes the first two rows and repeats them down below. So it's a little bit different than what I'm used to, but we'll do it that way. So 3 minus 2 minus 1 minus 4, 7 minus 1. And then what you do is you say this number times this number times this number, that's a number, plus this, plus this times this, minus, going backwards, minus this number, this product, minus that product, and then minus the third product. So let's go ahead and do one of them. So I want to multiply these three, and these three first. So let's do it. So this equals 3 times 7 times 1 plus minus 4 times 3 times minus 1 plus 2 minus 2, minus 1, and then minus, go in the other direction here, you're going to be minusing this diagonal times this product of this diagonal and product of that diagonal. So I'm going to be minusing 2 times 7 times minus 1 minus 3 minus 1 minus 4 minus 2 1. And after I do all that math, and I believe that the textbook gave you the right answer, you will come up with the answer of being 10. And so then now you have to do the determinant for each one of the variables that you're trying to find. So determinant 1 equals, and you rewrite it, you take 12, 0, 0, and you substitute it into the first column here to find V1. So I would write 12, 0, 0, minus 2, 7, minus 3, minus 1, minus 1, 1. Determinant of that over that big determinant of the coefficient matrix that I just found. So you do the same kind of a process again, and you will get the answer of being 48 divided by 10, or 4.8 volts. You do the same thing, determinant 2. Actually, I want this determinant 1 divided by that equals V1. Determinant 2 divided by determinant of the coefficient matrix equals V2, which equals 3 minus 4, 2. Put the 12, 0, 0 in, minus 1, minus 1, 1, divided by determinant of the coefficient matrix, and you'll get 24 divided by 10, which is 2.4 volts. And you'll do the same thing, that equals V2. And you'll do the same thing for V3. And you'll end up that V3 is minus 2.4 volts. So that essentially means, if I go back and look at the circuit for a minute, that means that this voltage at V3 is actually lower than the 0 voltage that I established right here. So V3 is 2.4 volts below this 0 reference point that I established. Now I didn't work through all of the determinants. That was a bit tedious. I am also going to show that this one right here, I'm going to go through this again for a second. I learned it a little different in school. It'll give you the same answer. I learned that you did 3 minus 4, 2, 2, 7, 3, minus 1, minus 1, 1. And I did it by repeating the first two columns, 3 minus 4, 2, 2, 7, and 3, and then did the math that looks like this times this times this, this times this times this, this times this times this. These are the pluses. These are the minuses, minus this, and minus this. And if you look at my numbers, you will see that surprisingly, not surprisingly, but interestingly enough, you will end up getting the same answers. So you will it'll still give you the same answers. Well, let me check if it does or not. So that's 21. It might be that you have to be consistent all the way through. Let's check it. I'm going to make sure. 21 minus 4 plus 12 minus 14 so that's okay. Minus 9. Yes, it is the same. Okay, minus 8. Yes. That looks like a plus 8, and I have a minus 8. So we should go back and check that. I will go back and check that. But I'm not going to use video time to check my math. If maybe you spot it right away. So anyway, I learned it this way, and then you find that the determinant 1, determinant 2, determinant 3 using exactly this same column method versus the row method there. I have a feeling I have a mistake in here somewhere, so we have to check what I wrote wrong. Okay, my math mistake of mine in there. I will check it. Continuing on. Well, I paused for a moment and found where my errors were, and so I dropped a minus sign here. So I corrected that and propagated it through. It does calculate to 10. And then I, going from here to here, drop some minus signs again. So I corrected that, and the answer comes out to be 10. So indeed, it gives you the same answer whether you work your determinants with Cramer's rule this way or you work your determinants with Cramer's rule that way. Either one will give you the same answer, which I would have expected. But if you are at all like me, you are prone to dropping signs and making sign errors, which is exactly what I just did. So it is actually nicer to do this kind of a thing in a math program. So before I go in and do the math program, I am going to do a little something about matrices and matrix notation. This matrix equation that I've written here can also be written as pause. Okay, so about the matrix notation, sorry I had an interruption for a second, so I paused the recording. So a lot of times, and let me be consistent with your book, because sometimes there's inconsistencies between math books. So a matrix can also be written with a bold letter. So let me see if I can make this a bold letter. So in matrix notation, I could call this a matrix A, and then this vector right here, a vector of voltages, I'll call it a vector V equals B. So if these are all bold letters, it means matrix or vector. I could also write some of the ways that you see it written. Sometimes people say it's A V equals B in matrix notation. And then the last way you'll see it in literature, math books or textbooks, is sometimes A is written this way, but V as a vector is written with a little vector symbol on top equals B, and B is a vector as well here. So these are all different ways that you see it in literature. Now if I wanted to solve for vector V, I could, I'll make this go back into this notation. Actually, I'm going to stay in the bold notation. We'll stay in the bold notation. So A inverse, written that way, times A times a vector equals B. So I'm all in the bold notation. So this is inverse of A. There's a formula to convert the inverse of A, but it's, if I was just doing scalar things, it would be like saying, I'm changing my pens. If you have 5 and you multiply it times the inverse of 5, you get 1, correct? Similarly, if you have a matrix 1/5. This might be kind of tiny. Let's give a new slide here. So if I have a matrix 1/5, 1/5, 0, 0 times 5, 5, 0, 0, you end up with the matrix 1, 1, 0, 0. This is called the identity matrix. And so note that if I have 1, 1 times x, y equals AB, and I multiply this out, I have 1x plus 0y equals A, or x equals A, and this bottom column, bottom row, 0x plus 1y equals B, and you have y equals B. So this is a matrix A right here. This is inverse A, and then so A inverse times A times AV equals B. So when you solve for that, you can find out that the vector V, which is our V1, V2, equals, sorry, whatever you do to the left side, you better do to the right side, right? Vector B equals A inverse B. Go back a slide for a minute. I didn't put the order is important here, so I need to make sure I wrote that right. Doesn't like to erase too well. Can I just select this object and erase it? Yes, I should be able to. No. So what I'm saying is I'm missing that equation wasn't quite written right, because if I multiply something times the left side, I better multiply it times the right side. So this is inverse A times V equals inverse A times B. So that allows me then to say this is now the identity matrix, a matrix of ones. Maybe it's a 3 by 3. Times V equals A inverse B, and so then you get V equals A inverse B. So I can solve for the vector B that way. So I'm going to do it to the example that we just did. We had that we have, recapping, we have the matrix A is 3 minus 2 minus 1 minus 4 7 minus 1 2 minus 3 1. This was the equation V1 V2 V3 equals 12 0 0. Now there is a formula for finding A inverse. So you can find A inverse, or I can go ahead and say that I will find A inverse, but I want to use a math program, so that's what I'm getting at. So I'm going to multiply both sides, in order matters, both sides by A inverse. And I'll have a solution for B. So let's show how to do that in a math program. So I'm going to use Mathematica. This is Mathematica. I hope you get Mathematica. This command window is where you can do real-time calculations, and I'm going to call my matrix A equals, and this is how you put in a matrix in MATLAB. 3 space minus 2 space minus 1. That's row 1. Separate it by a semicolon. Minus 4 space 7 space minus 1. Separate row 2 by a semicolon. And then minus 1. Oh, last row. 2. Sorry, it's 2 minus 3 and 1. Put a semicolon at the end. So those of you who are taking any C programming classes, you end up always with a semicolon at the end. Looks sort of familiar. So now I have specified the matrix A. Press enter. Over here on the workspace side, the matrix A is also shown over there. Then I'm going to say the matrix B equals, and it's a vector really, 12 space 0 space 0 space 0 bracket semicolon enter. Now let's say these are variables or constants that are now stored in the MATLAB window, but let's say I made a mistake. So I can correct it not by going back. I can't go back with my cursor, but I can redefine something. So B equal, I can put my cursor, press my up arrow, and get the things that I've already done. So if I messed up on B, I'm going to click on B. It came back in. There's B, okay. And now I can edit it and do whatever I want with it until I press enter. Once I press enter, it's done. So I have B, and I want to solve for V, the vector V of voltages. So I say vector equals inverse A times B, and I solve for it. Oops. Where did I mess up? 3, a 3, a 3, and a B is a 12. Oh, okay. These are, the way I've written it, I know what I did wrong. These are written, this is written as a row vector right now, and I need it to be a column vector. So I'm going to push the up arrow, find that statement where I messed up. There it is. If I want a different statement, I can select a different one. See it showing up on the current line. This is the statement that I messed up. The reason is that B has to be a column vector, so that's a transpose. It needs a transpose mark in it, which that means transpose. Transpose the vector from a row to a column. So now I press enter, and it calculated the result. I see the result over here on the right hand side, but it didn't show here in my main window, and I wanted it to, so let's do it again. I'm going to take away the semicolon, because semicolon means don't show me the output. Press enter, and there's the answer. Okay, so that's using MATLAB. Barely an introduction to MATLAB, but I just showed I can use a function called invert. It will invert my matrix A. I can use transpose to convert a row vector to a column vector, or vice versa. And I solved the problem in MATLAB instead. So the nodal analysis that we were just doing depends on Kirchhoff's current law. And in the circuit that we were analyzing, if I go back and look, the circuit that we were analyzing has nothing but current sources in it. So we were able to write our node equations, and we have current sources, and it was okay. Well, what if we have a voltage source in there? How do we handle it then? So that's what this section talks about, section 3.3, nodal analysis with voltage sources. So you can see there's two voltage sources in this circuit, and we have two different cases that we could address. One is if the voltage source is connected between the reference node and some other non-reference node, then it's pretty straightforward that the voltage is the voltage of that source. So I have a reference node right here. That's my 0 volt place. This voltage source is connected between this node and the 0 reference place. Therefore, the voltage here is 10 volts. It's also, you could just think of it sort of as I'm at 0 here, I rise up 10 volts, and therefore V1 equals 10 volts. So that's that case 1. Case 2 is I have this voltage source that's connected between two other nodes, and it's not one of the reference nodes. So I don't know how to treat this. I can't write KCL in this equation because I don't know what the current is here where the 5 volts there is, and because it's a voltage source, it can supply any current, and we have no way of knowing it because we can't say this voltage minus this voltage divided by some resistance here. There's no way to do that. So what we do is we create a thing called a super mode between this node 2 and node 3. This is a combination node, if you will, called a super mode. This super node, you can't call it node V2, V3. It doesn't really have a node voltage on its own, and you have to use a combination of both KCL and KVL. Also, this voltage being in the circuit is going to make an additional constraint equation, so then you're going to need that in order to be able to solve for this equation, solve this circuit, analyze this circuit. So here's the circuit. I redrew it again over here, and if I were to go, we know V1 is 10, so that's not too bad. V1 is 10. We can put our signs on. We should put our signs on, plus, minus. I4 they have going this way, so that's exiting a node. That's minus, that's plus. Keep us consistent here. Plus, minus, plus, minus. And we don't know what's going on right here. So we can write a nodal equation for the supernode, and what we have is I1 goes in, I2 goes out, I3 goes out, and I4 goes in. So I write a node equation for that supernode. That's fine. I can express I1 okay, V, which is 10 minus V2 over the 2 ohm resistor. I4 I'm okay. Where was I4? I4 was okay. V1 minus V3 over 4 equals I2, which is V2 minus 0, really, over 8 ohms, and I3 right here is V3 minus 0 over 6 ohms. Okay, no problem there, but I have V1, V2s, and V3s, and I have a node here and a super node here. So I need an additional constraint. So my additional constraint comes by applying KVL. So if I apply KVL, let's say around this loop right here, so this is, I'm actually picking a direction of, I'm not really, I'm just picking a direction to go around the loop and write KVL. And so I will have a voltage here. Since this is I2, I'm going to call that V2. And I have since this is I3, I'll call the voltage across this resistor V3. And so I'm going to go around the loop. I have, since I hit a minus sign first, I'm going to say minus V2. I have a plus sign going around the loop. I have a plus sign next, plus 5 volts, plus V3. equals 0. So V2 minus V3 equals 5. So this is an additional constraint so that you're able to solve for V1, V2, and V3, even though you will not have 3 nodal equations. You have a nodal equation and a supernode equation. So this is my additional constraint comes from there. Okay, let's do another example. This is example 3.3, but your book took some shortcuts that weren't obvious, so I'm going to work it a little bit more formally. This is page 90 if you want to look, because they took shortcuts. All right, so let's start by, we defined this to be our 0 reference point. So we have node 1 here, and well, this can't be a node. This right here has to be a supernode. So we will look at the things going in and out this supernode, because there's only a voltage in here. So that's our supernode. Let's go ahead and define some currents. This one's already defined for us. Let's call this one I1. So, and I'll put my markings here. Current goes in, so positive is here. This one's already given. I'll call this one I2. Put some polarity markings on it. And then your book kind of neglects this and says it doesn't matter in the circuit because of the 2 volts across it. That's true, but I think I will go ahead and formally define it so that you can see how it doesn't really matter. I will call this I3, and there's my polarity markings. So I will show you how it doesn't really matter. Okay, so now this is a supernode. We write the Kirchhoff's current law for the supernode. This is an in, this is an out, this is an out. But look, this is an out and this is an in both. But let's write it. 2 amps goes in, 2 and I3 goes in into the node, into the supernode actually. And then going out is I1. I3 is going out. And I7 is, or it's 7 amps is also going out. So voila, that I3 really doesn't matter because it both goes into and goes out of this supernode right here with the voltage source in it. So let's go ahead and write the equations. I have 5 equals, did I miss one? Yeah, I missed I2. I2 goes out. This is I3 goes in, I1 goes out, I2 goes out, I3 goes out, and 7 goes out. Okay, so 5 equals, well, let's say minus 5 equals I1 plus I2. So that's fine. That's a fine node equation. Now let's go ahead and say what these currents are. I1 is V1 over 2 ohms. I2 is V2 over 4 ohms equals minus 5. I will go ahead and make that a little nicer equation just to work with, and I get V2 plus 2 V1 equals minus 20. The other thing that I know is that, so I have, this is basically one big supernode, so I have one equation but 2 unknowns, V1 and V2, so I need an additional constraint, and I know that V2 minus V1 is 2 volts. V2 minus V1 equals 2 volts. So that was an additional constraint that I got from this supernode right here. And so now at this point I can solve my 2 equations and 2 unknowns. I think I'll just do it by substitution method or elimination method. Subtract these 2 equations and I get This minus this is minus 22, and then I get this minus this is 3v1 equals minus 22, so therefore v1 equals minus 22 over 7, which is minus 7.333 volts, and then v2 minus v1 equals 2, so therefore I can get my other voltage. So indeed it didn't matter what was over here. This 10 ohms actually never ever came into play in this problem. The voltage across this resistor is the voltage across this resistor, period. So let me go ahead and do the other, complete the problem here. So v2 minus v1 must equal 2, therefore v2 equals 5 minus 5.333 volts. So what does that really mean when I say minus? That means that this is a zero reference point where my ground is, and that this voltage here is lower in potential than my zero reference point is. Okay, that's long enough for this video. The next video will be mesh analysis.